Welcome to Chapter 8, Section 4, Calculating the pH of Solutions, starting page 298. Hopefully to this point you've learned about acids and bases and you've seen how these are important to our environment, to just life in general, our bodies as well. And at this point you should know about strong acids, strong bases, know about the pH scale. So the pH scale is from 1 to 14. Neutral is 7, pH of 7, and anything below 7 is considered to be acidic pH, and above 7 is considered to be basic. And now we're going to look at calculating the pH of solutions. And so remember, pH corresponds to the acid. It corresponds to hydronium concentration. So our hydronium is H3O+. The calculation that you will, or the equation that you need to know, and this was kind of wrapped up in one small video previous to this one, but the pH is equal to negative log of the hydronium concentration. Okay, and for strong acids, all we have to do is we can just take the molarity of a strong acid. So we'll see that here in a few minutes. You just take that number and you take the negative log. So if we have a solution that has a hydronium concentration of 1 times 10 to the negative 4, all we do is we take negative log of 1 times 10 to the negative 4, and that gives us a pH of 4. Okay, some of you have different calculators. You may need help with this. Your book does a pretty good job, as well as through the course material, kind of showing you how to plug into your calculator. For those of you that have graphing calculators, as I do, you really just use negative, and then log should be kind of over on your left-hand side, possibly, depends on what calculator. And then you use parentheses. So be sure you're using parentheses to encase the hydronium concentration, and you should get 4 as your pH. And what we do for pH, if we're given how many ever significant digits we're given for the concentration. So here we have 1 because it's 1 times 10 to the negative 4. So that 1 is considered that we have 1 significant figure. And so we report our answer to 1 decimal place. So this is a little bit different than what we've seen previously with significant figures. So how many ever significant figures you have, you're going to have that many numbers after your decimal place. Okay, and so if we had another solution that had a hydronium concentration of 8.0 times 10 to the negative 6, if we plug that into our calculators, okay, so some of you may have to, depending on what calculator you have, let me know if you're not getting the same answers here. But we start out with 2 significant digits as 8.0, and so we're going to have 2 decimal places, and so we should get 5.10. We take the negative log of 2.4 times 10 to the negative 8, we get a pH of 7.62. Okay, so you can check this on your calculator as well. You want to be sure you're getting the same answers. And if we round to 2 decimal places, we round up to 7.62. Okay, this is just a guide to enter the hydronium concentration. For those of you with calculators that are not graphing calculators, you enter the concentration, then you press the log key and change the sign, and then you adjust your significant digits. So this kind of goes through and shows. But for those of you that have graphing calculators, like I do, really you just put negative log and then put in the number. Okay, and so here, so you can read this, you can go through and do this on your calculator, but the key here is that we take negative log to find the pH equal to 1.0 times 10 to the negative 3. Okay, so if you plug this into your calculator, it goes through and tells you can actually enter the number and then press the EE on your calculator, change the sign. So this is for actually the most complicated, I would think, any of your calculators could be with respect to these calculations. And then if you adjust the significant digits, so if we take the negative log of 1.0 times 10 to the negative 3, we're going to get 3.00. We had two significant digits, and so we need two decimal places, or two numbers after the decimal place. Okay, so easy enough here if we've got we want to know the pH of coffee, and it's got a hydronium concentration of 1 times 10 to the negative 5th. Okay, you don't even have to use your calculator. Whenever you have just a 1 here, then this negative 5 kind of corresponds also to a pH of 5. But if we plug it in, so you want to get practice in plugging in. So we take the negative log of this number, and we get a pH of 5.0. We have one significant digit, so we need one number after our decimal place. Okay, and if you were given, let's say, we want to find what is the pH of hydrochloric acid. Okay, and you want to keep in mind that we're not going to try to trick you or anything with these, but in order for us to use this equation, we have to be dealing with strong acids, okay, because they completely ionize, and so whatever their concentration is also equal to their hydronium concentration. So if we were to say that we have a 0.100 molar HCl solution, okay, remember the big M is equal to molarity. So this is a way to describe concentration. Okay, these brackets that are around this number here, this also means concentration. So this is the concentration of the hydronium in the solution or in the coffee. Okay, but if we wanted the pH of a 0.100 molar HCl solution, okay, and what we can do is this number here, our molarity, this is equal to our hydronium concentration. And that is because strong acids completely ionize. Don't let this confuse you. If you're not given a number that's shown here saying hydronium concentration is 1 times 10 to the negative 5th, here up in this problem, okay, you can also just be given that you have a 0.100 molar HCl solution. Because it's a strong acid, then you can just use that number. So we would take the negative log of 0.100 and that gives us a pH of 1. Okay, so let's do another one real quick. What is the pH of a 0.215 molar solution of nitric acid? Once again, this is a strong acid. We have nitric acid. And since it's strong, we can actually just take the concentration and take the negative log of 0.215. This is just showing you two ways that you could be asked this question. So you can be given the hydronium concentration is, or it can be given to you in the problem as, you know, a molarity or a concentration. So we have 0.215 molar. So if we take the negative log of 0.215, we get a pH of 0.660. So we're given three numbers, three decimal places, so about 668 if we round up. Okay. Another practice problem. tomato juice has a hydronium concentration of 2 times 10 to the negative 4. So if we take the pH equal to the negative log of 2 times 10 to the negative 4, we have one significant digit, so we're going to have one number after our decimal place. So if we take the negative log of 2 times 10 to the negative 4, we get 3.7. So if we round 69, it's going to round up to 3.7. So we have one number after our decimal place. Okay. We can also be asked to find the pH if we're given the hydroxide concentration. Okay, and so what we have to do here is we have to remember from the previous videos our ion product constant, that hydroxide concentration times the hydronium concentration. Okay, hydroxide is representative of a base, hydronium of an acid. And this is all due to the fact that water can act as an acid or a base. But this number is a number you want to be sure that you know, 1.0 times 10 to the negative 14. Okay? So if we're given a hydroxide concentration, we can rearrange this equation and we can solve for hydronium concentration. And then once we know that, we can take the negative log and we have our pH. So we need to know pH. This is going to be a two-step process. Okay, so we're going to be looking for hydronium concentration. So we're going to isolate it over here by itself. Okay, and now we're going to plug in the hydroxide concentration. And this is going to give us the hydronium concentration. So if we take 1.0 times 10 to the negative 14 and divide that, okay, remember that you need to be sure you're getting the same answers. There's a lot of calculator issues here. And most calculators want you to put these numbers in parentheses. Okay, and so we end up getting 2.1, so we'll use 2.1 times 10. I was looking at significant digits here. So we've got 2 in both, so we should have our answer in 2. So this gives us the hydronium concentration. And now we know if we take the negative log, we can find the pH. So if we take the negative log of our answer here, we get 11.67. And we have 2 significant digits, so we need 2 decimal places. So we round to 11.67. Another thing to remember here, your book doesn't go into a lot of detail about pH and pOH, but pH deals with our acid. But we can also, since our scale is out of 14, we can also just say that basically pOH plus pH has to equal 14. So that's our scale. And so pH, if our pH is 11.67, then basically we can also solve for pOH. We will want to look at the pOH of a basic solution. And so our pOH would be 2.33. So as you're practicing these, you'll see that you can use your ion product constant. So this here, this equation, your pH is equal to negative log of hydronium concentration. And then this is important too, because your scale is out of 14. Okay, and you can use all 3 of these, and then we're going to talk about the way we rearrange one equation here in a minute to use it. But you can use all these, and you can basically solve for pH, pOH, hydroxide concentration, hydronium concentration. So you can just kind of interconvert these, and you can actually do these, do some problems in there's more than one way to do them. This concludes the video on calculating the pH of solutions And next we will cover calculating the hadronium concentration from pH. Thank you.